graduated somewhere in the mid-80s from here at University, and joined, I believe he went to Hinton, in Toronto, then worked for a while with NEC.
Bell Labs first.
Bell Labs first, and then when Bell Labs became crowded, or less crowded, he moved to NEC, and now you are with NYU, right? Some sort of mathematics. I know Yann because of his work in machine learning and non-linear machine learning, modern methods of machine learning. Our class finally crossed last summer in Telluride, where he gave excellent talk on deep learning, and I thought that it would be very interesting if he can tell us a little bit more about what he's doing now, and I see that it's still related to deep learning. Yann LeCun.
Thank you. So I suppose I need to turn this on, right? Oh, it's on already. Great. So yeah, it feels like AT&T here. I see a lot of
I told you so.
a lot of familiar faces. Right. So I'm going to talk about learning features, and it's sort of an unusual thing to do for someone working on machine learning. Most people who work on machine learning talk about learning classifiers and things like that. But I'm going to talk about learning features. And there's a big cast of characters that has participated in this project. So one of the things I'm interested in is the sort of next big challenge of AI or robotics, neuroscience, computer vision, perception, artificial perception in general. And how do we learn perception? How do humans or animals learn perception? How could computer learn perception as well? And part of the things that humans and animals seem to be able to do is to learn representations of the perceptual world. So with sort of fairly minimal prior information to sort of figure out how to represent the world so as to be able to navigate in it and pick out objects and recognize objects and classify, prey and mates and things like that and food. So, how are we able to do this? And we're able to do this after a few months or years of training. We can be trained to recognize new categories with just a very, very small number of examples being shown. So a lot of children are taught to recognize animals by, having cartoon drawings of them in picture books. And, how is that possible? So the sort of classical way of doing pattern recognition and computer vision in particular is you take an input image, you run it through some sort of pre-processing that extracts appropriate features, and generally this process is done by hand. You sort of design the feature extractor by hand so as to eliminate the irrelevant information and variability from the input, and sort of, make it more digestible by a sort of more generic classifier. And then the classifier on top is your favorite classifier du jour, and you kind of train it with your, favorite supervised learning algorithm. And the problem with this, of course, is that you have to come up with this module for every new problem you're trying to solve. And a big percentage of the computer vision and speech recognition and pattern recognition literature in general is devoted to this aspect of the problem. So if you look at how the visual cortex is organized, and there's a similar picture for the auditory cortex, it's a very hierarchical system. You go from the retina to lateral geniculate nucleus to V1, V2, V4, the infratemporal cortex, and every step of the way, the representation of the world is transformed into sort of a more abstract representation, a more kind of global representation. So at the low level, you have kind of local features like edges, and then in the middle, you have more like little textures and parts of objects, and then at the high level, it's more objects and scenes and things of that type. So there's this sort of hierarchical process by which the representation is sort of distilled, if you want, as you go up the layers. And so what I'm proposing is a fairly similar architecture that we should train, that consists in sort of a number of kind of a cascade of boxes, each of which you can think of as a feature transform, something that turns the sort of relatively low-level representation at its input into slightly higher-level representation on its output. And you kind of have a whole bunch of those. And it's terminated by a classifier. So for images, you can think of going from pixels to edges to text on parts, object, scenes. For language or speech, it could be for language, it could be words, part of speech, sentence, text, things of that type, or attributes here that contain semantics as well. And you can construct sort of a number of hierarchies like this for every perceptual task that you can think of. So the main problem with this approach is that we're going to have to come up with learning algorithms that allow us to train those deep architectures. Okay, with deep in the sense that they have multiple stages in them. And that might be a little complicated. So the whole problem of deep learning, which has become a bit of a sort of a trend in machine learning over the last 4 or 5 years, is the problem of learning a hierarchy of sort of nonlinear transforms that way that essentially are able to learn good internal representations of the inputs. So here is how sort of classical, what has become the classical way of doing object recognition works. So that's the architecture of most recent object recognition systems for vision. So you start with an image, you apply a bunch of filters to it, say edge extractors, then some sort of nonlinearity after that, and then an operation that I would call feature pooling, which basically combines the filter responses in a small area over the input, and sort of eliminates a little bit of position information about the features. And you can stack multiple stages of this sort of basic stage, multiple instances, and then stick the output to a classifier. And this sort of basic idea comes from neuroscience. The computer vision community has kind of brought itself to accept the fact that a lot of the best methods are actually indirectly inspired by neuroscience. A lot of people would not admit it, but that's really a fact. So neuroscientists would clearly identify the first two stages, the first two layers, as what they call simple cells. And the remaining stage or layer within the stage as complex cells. And I'll say a little bit more about what those models are. So this draws from classic work in neuroscience, visual neuroscience, by Hubel and Wiesel in the 50s and 60s. And it's relatively obscure work that received a Nobel Prize. So it's not like it's really that obscure. So things like very popular feature extraction methods in computer vision, like SIFT, GIST, HOG, and things like that, are essentially directly inspired by this. So here is the Hubel and Wiesel cartoon picture of how you extract features. So you have, say, an image. Here I draw 2 images, maybe 2 channels from an image, 2 color channels or something like that. But let's just think about one. You apply a convolutional filter on it, and the result of it is some sort of resulting image, which is the response of the filter at all locations, right? It's just a convolution. And if you have multiple filters, each filter will produce a different feature map, okay? So each plane here is called a feature map. And after you transform those through some nonlinear pointwise transformation or something a little more complicated, you get sort of, those things indicate the presence or absence of features at a particular location in the input. And if you take a kind of a slice of a particular location across all feature maps, you can think of it as a feature vector that represents this particular location on the image. So then the pooling operation essentially is it's subsampling with averaging. You can think of it this way if you're a signal processing person. So you would take a little neighborhood of the response of one of the filters, sum up the outputs, or maybe compute a max of the outputs, and then put that at the corresponding location on the output here. And then the stride by which you would displace this window would be more than 1, so you would subsample the result here from what you had here. So what you have now is a lower resolution version of what you had here. And you do this for each feature map independently. So what you have here is that you have exchanged spatial resolution for sort of feature resolution, if you want. Okay? So you can stack multiple stages of this kind of operation, and when you have multiple channels that need to be combined to produce feature maps, you just apply multiple convolution kernels to each of those maps, and you add up the result into a single map. Okay, so here, if we have n maps here and p maps here, we'll have n times p convolution kernels to kind of go from here to here. Or you can kind of subsample this in a sparse way. So this type of architecture, which you could call it a multi-stage Hubble-Weasel architecture, really. I call it convolutional nets because it's sort of a neural net-like architecture where the basic operation is a convolution. Okay, so hence the name convolutional net. Other people had ideas similar to this with different learning algorithms. So there's a question of how you train this, and we're going to train this with a combination of supervised and unsupervised learning. But I'm going to start by talking about how you train this in supervised mode. So here's an example of one of those convolutional nets in action for object recognition. A bunch of feature maps are extracted here, 64 filters, subsampled version of them, and then another bunch of feature maps, each of which is connected to a subset in the previous layer. The subsampling layer I'm not showing, and then the output. And the filters here have been trained. Okay. So what we're going to do is we're going to train those things end to end. And there's a whole bunch of people working on this sort of approach to vision and audio. So people have been sort of applying similar architectures to speech recognition, speaker verification, genre recognition for music and things of that type. So in particular, my colleague Rob Fergus at NYU, Jeff Hinton in Toronto, obviously, who is kind of the guy who kind of started the whole thing, Andrew Ning at Stanford, David Lowe at UBC, Tommy Poggio at MIT, although is using a very different way of training those systems, but the architecture is very similar. And then there's so Thomas Sayre is a former student of Tommy Poggio, who's now at Brown. Larry Karin, who's a signal processing person at Duke, who's done some really interesting work on sort of the mathematical side of this, as well as Stéphane Mallat, who is well known for his work on wavelets, and Sébastien Song at MIT. And then there's a whole bunch of people in industry at NEC, Google, France Telecom, Microsoft, and various other places, which I'll come back to that a little bit. So how do we train convolutional nets with supervised learning? So this is an example that's drawn from some work I did at Bell Labs many years ago. So this is an example of a convolutional net trained to recognize handwriting. And here I'm sort of translating this little digit here and showing the internal state of this network for sort of various translated versions of this digit. And what you can observe is that the sort of high-level representation of this digit sort of changes in very simple ways compared to the type of changes that happen here. So it's relatively easy to stick a classifier on top of this to get sort of good performance. Okay, and the way we train this is going to be just supervised. Stochastic gradient descent using the backpropagation learning algorithm to compute the gradients. Very simple. Okay, so you stick an input, propagate through, compute the difference between or the error between the answer you get and the answer you want. Using a backpropagation procedure, compute the partial derivative of this loss function with respect to all the parameters, update, and do that with stochastic gradient. It's been known for 20 years. So you can use this to, train phase detector with the obligatory Star Trek slide. Two of them, and works really well. Works quite a bit better than the thing you have in your digital camera, which is kind of a variant of Viola-Jones. We even have code on the web. You can train your own phase detector if you want. This is kind of a C++ library and scripts that allow you to do this with convolutional nets. It's a library called EBlearn. You can do object recognition, and I'm going to skip this a little bit. And you can apply those convolutional nets to fairly large images to do kind of simultaneous recognition and segmentation. You can also do this to use this to do image segmentation. And this is not work that was done in my lab. This was done by Sébastien Song at MIT and his students, in particular Veer and Jane. And the problem they had to solve was to segment scanning electron microscope images of brain tissue, and they have kind of images of slices of brain tissue. So they have sort of a 3D image of brain tissue, and they want to segment the neurons from that system. And they did a really good job at this using convolutional nets. So let me actually show you you should have done a video of this because it's pretty cool. And so they used a 3D convolutional net. So the convolutional net takes a 3D neighborhood over this volume of images and is trained to label the central voxel as being either a boundary voxel, a sort of cell membrane, if you want, or inside or outside. So this is the kind of data they have, and they have slightly higher resolution in the XY direction and the Z direction, which creates some problems. And so they run this convolutional net, they get the boundaries, and then after that they can run a sort of various post-processing morphological operations, etc., and sort of connected component analysis in 3D to recover the neurons. So I believe this is a piece of retina tissue from a mouse or something like that. It's a big mess. But it works really cool, really well. So they want to use this for essentially reconstructing the wiring diagram of a fairly big piece of the brain, and they sort of far from that still, but they're working on this pretty actively. And they've compared this with sort of more traditional image segmentation methods, and essentially got much better performance than things like CRF or mean shift or things like that. Yes?
So in the case of classes and faces, it's sort of easy to understand what the convolutional net is doing, but here, what are the classes? Is just
so classes are membrane versus just class 1 versus inside or outside of neuron. Okay?
and then each one of the neurons is a different class.
Say again?
Each one of the neurons is a different class.
No. They don't classify the neuron. They just classify. Okay, so the dark stuff should be classified as 1, and the bright stuff as 0. Essentially, that's what it is. Okay, but it's very noisy and it's very difficult, and it's in 3D, and you have to use context. So the so the colors are after post-processing. So after you've identified the boundaries, you can run a connected component analysis post-processing. Yeah, they're just random colors to show the different neurons, and there are mistakes in it. And they use a very sweet trick as a loss function to train the system. I'm not going to go to the details of this, but it's a very cool idea. So there are commercial applications of those things of course, at AT&T, Lucent, NCR. Back when I was at Bell Labs, there's a startup company, a sort of spin-off of NEC called Villian Technologies, which uses that for tracking people and surveillance, video surveillance. NEC Lab has a whole bunch of applications of this, some of which are deployed, many of them in Japan, for things like intelligent advertising posters that recognize the gender and the age of the person in front of it. They do this for kiosk and advertising posters. So the advertising changes depending on the person in front of it, and the kiosk will offer you different drinks depending on who you are. And those are deployed. There's some publicity around it. They also use this for cancer cell detection in medical images. Google uses convolutional nets for face and license plate detection and removal from street view images. And Microsoft uses it for OCR, handwriting recognition, and things of that type. France Telecom has various applications in face detection, human-computer interactions, like automated, cameraman for video conferencing. There's various other projects, industry, and various other things. So one of the things we've been working on over the last few years is to implement this in hardware so we can run it at very high speed on very, very small computing platforms so that we can embed it into robots, particularly flying robots. We haven't done that yet, but we're working on this. And so we've been working on something we call NuFlow, and this is a collaboration with Eugenio Colucciello's lab at Yale. And it's sort of a data flow architecture, for those of you who know what that is. So the basic idea is that, so it's an example of an early implementation of it with a small FPGA. So FPGA is kind of a programmable hardware, if you want, reconfigurable piece of hardware. And it's directly connected to this camera, and this can run a fairly large convolutional net at very high speed. We have a new version that uses a higher-end FPGA. I'm going to show you a little bit about this. So the basic architecture of this is that it's a grid of tiles, and each tile is a little programmable processor. But it doesn't run instructions the classical way a processor does. It receives an instruction from sort of a controller, if you will, that tells it, now you're going to do multiplies, okay? And it only do multiplies. It doesn't interpret instructions. It's just configured to do multiplies. So you configure each tile to do a particular operation, and you configure the connections between the tiles from the top, and then you just pump data through this grid at maximum speed, and it just ripples through. And so you can configure this thing to do convolutions, to do nonlinear transforms, to do this subsampling operations I was talking about, to compute SIFT and hogs and whatever vision features that you want, and a number of other operations. We even have a compiler for it, so we can sort of describe our network in relatively high-level language, and then it gets directly compiled for this architecture and just runs. And so this runs on an FPGA, and right now we're developing a special purpose chip, full chip, which will have a performance of roughly 1.2 tera operations per second, consume under 5 watts, and be about 5 by 5 millimeters, which is fairly small for a chip. And it's got a big grid of those tiles on it. So some ideas of performance. And this is kind of running real convolutional nets on it. So this is not peak performance. This is the actual performance we would get when we run the thing. So it would be about, so this is with actually the previous technology we thought we were going to use, so it's slightly slower. But it would be about 1,000 times faster than a software implementation on an Intel processor. And, roughly 5 times, 3 times faster than the fastest GPU. But the GPU consumes 220 watts, and this guy is going to eat about 2 or 5 watts. We don't know yet, something like that. So we can put this on robots, toys, things like that. We'll see. So this actually caught the eyes of, I'm going to brag a little bit here. So this caught the eye of some journalists at The Economist, and they wrote an article about a month ago about robot vision and stuff like that, and it was all about convolutional net. And so the journalist, I spent an hour talking to him about what a convolutional net was, and he came up with this description in one paragraph of a convolutional net for a layman audience, and it's beautifully written. It's like really clear. I wish this guy was writing our papers. It's fantastic. Okay, so how are we going to do object recognition with convolutional nets? Like real object recognition. So here is the sobering thing that we noticed about 5 years ago. So the computer vision community came up with this data set called Caltech 101, which is a relatively small data set of objects collected from the web, object images collected from the web, about 100 categories, 101 categories, and 30 training samples per category. Very, very small, only 30 training samples per category. And of course, the computer vision community, use, handcrafted features and stuff like that. So, you don't need a lot of training samples, and it's, inconvenient to collect it. So it was perfect for those vision algorithms, but not so good for convolutional nets because they need a lot of data to do a good job. The handwriting is, tens of thousands of examples. Face detection is, typically 50,000, things like that. So here with, only 3,000 samples, we can do a good job. So if you just train a supervised convolutional net of the type I just described, you get something like 29% correct on Caltech 101. And back 4 years ago, something with SIFT features and very simple classifier on top with, vector quantization and pooling and simple SVM on top would get almost 65%. So that's really embarrassing. So we thought it was because there was just not enough training data, right? So we started getting interested in unsupervised learning to be able to take advantage of a large collection of unlabeled samples to get better performance. It turns out we were partially right in doing this, and I'll go through that a little bit. Before I do that, I'm going to tell you a little bit about this 65% accuracy method from Lana Lazebnik, Jean Ponce, and Cordelia Schmidt. So it very much conforms to this architecture I was telling you about before. The filter bank are oriented edges. The nonlinearity is a winner-take-all with a little bit of blurring. The feature pooling is just a sum, a histogram. That's the SIFT operator, and that's applied densely on the image. Second stage is basically vector quantization, k-means. with a nonlinearity. So nonlinearity is basically winner-take-all. The filter bank is the prototypes of k-means. And the feature pooling is just this kind of pyramid histogram. It's very simple addition. Classifier is a supervector machine. Okay, just a simple one. So this is fixed. This is trained unsupervised with k-means, and this is trained supervised. Okay, and with that you get 65%. And when you look at the architecture, you say it's not that different from a convolutional net. Why can't we do the same with a convolutional net? So we set out to use this deep learning ideas of using unsupervised learning to do a better job at this. And this is sort of following some idea by Jeff Hinton about 5 years ago. And this kind of, Yoshua Bengio, my lab, and Andrew Ning's lab at Stanford have been working on this since then quite extensively. So the basic idea is to use unsupervised learning to pre-train the architecture to get good features, and then use supervised learning to just refine to kind of fine-tune the result to get labels out, right? So it's based on the idea of sparse coding. So sparse coding is a increasingly popular method for learning features, and it's the following thing. You take an input vector. Imagine it's a patch on an image, a patch of an image, or say an acoustic vector if you do speech recognition. And you're going to try to represent this input by minimizing a square reconstruction error. And the way you represent it is as a weighted sum of basis functions or dictionary elements, which are the columns of those WD matrix, by a coefficient vector. And that coefficient has a sparsity penalty on it. So the sum of the absolute values of the component is one of the term in the energy function. So you're going to minimize the sum of those two terms, the sum of the absolute values of the components and the square reconstruction error with respect to z. So if I give you a y, if you already know WD, I give you a y, you find a z that minimizes the sum of those two terms, this function if you want. Okay? And what you'll get is a good sparse reconstruction of y as a weighted sum of a small number of columns of WD. Okay? That's sparse coding. And then there is sparse modeling. Sparse modeling consists in learning this dictionary matrix by minimizing this loss function, which is essentially the sum over training samples of the minimum energy you get by finding the optimal code for each input vector. Okay? So you plug an input, find a z that minimizes the sum of those two terms, and to minimize this loss, you tweak the parameters in WD so that the square reconstruction error is decreased. Okay? And you have to have an additional condition, which is that the columns of WD have to be normalized, otherwise everything diverges.
You learn WD?
Yes, that's what I just mentioned. Yeah, you learn WD using gradient descent. Minimizing this loss. Okay. So here's the problem. If I give you a y, it's going to take you a while to give me a corresponding z, because you're going to have to minimize this little L2, L1 energy function, right? And you're going to have to do this for every patch on the image, and z might have a couple hundred dimensions, maybe a couple thousand. It's going to be really expensive. You're not going to have a real-time vision system if you do this. So there's a lot of efficient algorithms to do this, that come from the applied mathematics literature, but they're still not good enough. So here's an idea. The idea is that you're going to train a feed-forward predictor to predict the solution of this sparse coding problem. Okay? So you plug it. So you plug a z, a y. You find a z that best reconstructs this y under the sparsity penalty. Okay? And now what you have is a y and a corresponding optimal z. You're going to train a feed-forward machine, a nonlinear predictor, if you want. Think of it as a simple neural net, let's say, parameterized by those parameters WE, to minimize the square reconstruction error of z given y. Okay? So once this guy is trained, it's going to, if you give it a y by just a very simple feed-forward propagation, it's going to compute an approximation to z. And it may be good or not, but it's, if it's good enough, it's good enough. So so I'm skipping on the details. So the architecture of the little box we use inside of this predictor, we use sort of various architectures, but the latest one is based on an algorithm that we know converges to the correct answer if we run it long enough. It's called the FISTA algorithm, Fast Iterative Shrinkage and Thresholding algorithm, that comes from the applied math community. So what we do is we sort of unfold this algorithm, if you want. It's an iterative algorithm. We'll unfold it for a couple iterations. And what we get is sort of the result of running this for 2 iterations. But the FIST algorithm specifies which matrices we have to use here. And instead of setting those matrices to those specified values, we're just going to run them so that our prediction is as good as possible. So we're going to view this as a feed-forward network that we're going to train with backpropagation. We're going to train this matrix, train that matrix. And we're going to train it so as to give us the best possible approximation to the sparse code. And it works really well. It does a very good job. I just skipped the results, but it does a very good job at predicting sparse codes with sort of very limited computational resources, essentially in a feed-forward manner. Okay, so if you apply sparse coding to, say, handwritten digits, the dictionary elements you get, which are the columns of this WD matrix, or the WE matrix, actually, they look very similar, are little parts of characters. And the reason is that you can reconstruct any digit as a linear combination of a small number of these guys, okay? And so they end up being little strokes, because that's the best way to decompose a digit into sort of a small number of parts. So this is the learning algorithm running on natural image patches. And again, these are, each little square here is a column in the WD matrix represented as an image, or as a kernel, as a kernel of a convolutional filter, if you will. And what you get at the end are essentially Gabor filters. So this is an example of a result. The filters are Gabor filters, okay? And so you talk to neuroscientists and they tell you, well, you know, that's kind of what we find in V1 in the visual cortex of mammals. Not so surprising, but there's lots of algorithms that will give you Gabor filters. Okay, so here is how we're going to use this to train a convolutional net, or to pre-train a convolutional net unsupervised, okay? We're going to use one of those little encoder-decoder system with a sparsity constraint, and we're going to train it on image patches, right? Once we're happy with it, we get rid of the decoder. We only keep the feed-forward encoder and the absolute value. And what we get here is a vector of rectified sparse feature vectors for a patch, okay? We apply this to all patches in an image, and what we get here are feature maps, like the first layer of a convolutional net, all right? That's going to constitute the input to our next layer. So normally we would have a pooling layer here, which I'm not representing, but we're going to stick a second layer on top, and again do the train it unsupervised using this little encoder-decoder architecture. You know, learn the WE and WD. When we're happy with it, get rid of the decoder, just keep the feed-forward path. And now we have 2 stages of feature extraction, trained completely unsupervised with unlabeled data, just images collected from the web. All right? Stick a classifier on top, and then train the classifier supervised, or even train the entire architecture supervised. So refine, you know, using backpropagation, refine all the parameters all the way through using supervised learning. So that's, you know, basically an example of deep learning or deep belief nets or whatever you want to call it. So let's apply this to object recognition with convolutional nets. So here's an example of filters that we get when we train on natural image patches. 64 filters in that case. Run that through the convolutions. Here the nonlinearity we use is a hyperbolic tangent followed by an absolute value. And then we're going to add another little twist here, which is a sort of a nonlinear stage that we call local contrast normalization. What it does is that it takes every value in this sort of 3D array of feature maps, if you want, and it replaces every value by itself minus a weighted sum of its neighbors, okay, a weighted average of its neighbors. So it's kind of like mean removal. It's sort of like a high-pass filter in the feature space, if you want. And what we're going to do next is that replace each value within this 3D feature map by itself divided by the standard deviation of its neighbors across space and across features. Okay? And that is going to sort of do a little bit of whitening, if you want, sort of equalize variance of all those things. So we call that subtractive and divisive contrast normalization. And then the pooling layer. So that constitutes one stage of a recognition architecture, and we can stick 2 stages of that on top of each other. And so to make a long story short, here is the results that we get. So here is the good news. The good news is that we get something like 65.5%, which is pretty much, you know, a little better, but pretty much the same as what Lana Lezebnik was getting 4 years ago. with SIFT and k-means and purely match kernel and super vector machine on top. So the result I was telling you about before of a classical convolutional net trained with supervised learning is here, 29.7% correct. And so that's using so-called average pooling and just hyperbolic tangent nonlinearities. And the difference, but here's and this is trained with a purely supervised way. So R plus here means random initialization of the parameters, and plus means supervised training. Okay? U plus means unsupervised pre-training using this little encoder-decoder architecture, and plus means supervised refinement. Okay, so UU is simply unsupervised learning with no supervised refinement. Only the last layer, the classifier, is trained supervised. R means completely random filters, so the filters are not trained at all. Okay, just random values. And this is using Gabor filters and sort of template learning, similar to Tommy Poggio's and Thomas Serre's HMax model. Okay, so the good news is we can match the performance of the sort of handcrafted system. But unsupervised pre-training doesn't help that much. It only brings about 1%. If we just use supervised training, it still works very well. And the difference seems to come not from this unsupervised training, but from the fact that we have those nonlinear stages inside of the architecture. So here, the classical convolutional net, as of 15 years ago, was using hyperbolic tangent nonlinearities between layers, and that's about it. This guy uses absolute value rectification of the features, so we only get positive features. This contrast normalization I was telling you about before, and just those two nonlinearities boost the performance by a factor of 2. It's ridiculous, and it's hard to believe. And I couldn't believe it actually initially, so we had to sort of double check. Here is what's even more incredible. What's incredible is that if you use completely random filters with these nonlinearities of absolute value contrast normalization, you still get 63%. So much for learning, right? So my students produced this result. So first of all, I didn't believe it, and so we sort of did it multiple times, and then, after that they were totally depressed because they worked for years or months at this sort of sophisticated unsupervised learning thing, and they get this tiny improvement. RR is completely random filters, no learning on the filters, just right. Now here is the thing though, if you don't have the right set of nonlinearities, performance is ridiculously bad, right? 8.8%, it's really horrible. So there's something magical about those contrast normalization somehow and rectification. And so I go across the street to my friends in the neuroscience center at NYU, and I said, can you explain this? They said, yeah, we've known this for a long time. I said, well, why didn't you tell me before? I said, we told you so before. You didn't listen. That's kind of embarrassing. Right, so it's good news and somewhat bad news. So I should say, this is actually, it turns out, it's a fluke of Caltech 101. So on other data set that I'll show you later, you don't see this, okay? So in fact, the latest result is that we got something like 71% correct, and I'll come back to this a little bit. Let's see. Okay, so before I say too much about this, let me show you a demo of this system. So I've got a webcam connected to my laptop here, and it's grabbing images, and I can train it to recognize things. So this is a telephone. Okay, so I'm going to hit the T key. Okay, and I've stored 2 templates of this telephone, and it's red because it's recognizing this as a telephone. So if I point the camera to something else, it's not a telephone. If I point it here, it's a telephone. Face. Okay, so this is not just a face. This is Yann. All right. Okay, and this is still a telephone. And this is what is this? Rubber band. Rubber band. So I didn't bring those objects, right? These are random objects on the table here. And this is a bad reflection here. Another face? Okay. Someone wants to come here? Okay. Oh, I'm sorry. My demo crashed. There's a problem with the driver for this webcam, unfortunately. So, ooh, okay, here we go. Let me start again. It doesn't usually crash. Okay, let's do this again. So, this is Yann. This is the telephone. This is the chalk box. Rubber band. And you're just a face, okay? You're F, all right. So you're F. Still rubber band. Still telephone. You know, with quite a bit of robustness. Still chalk. Let's try the water bottle here. Water. Okay. Room. Okay, the audience. All right.
Let's try something else. Let's put the water bottle on the other table.
So, okay. So that's probably not going to work because the camera is going to get totally saturated by the white here. Okay. But let me try to put it someplace else, perhaps here. Yeah, it works. All right. And it's transparent. And it would probably work with another bottle if I had another one. Okay, but you guys. Okay, so let's see if we can use this to for a robot to find out landmarks. Okay, so you guys are 1. Okay, on the left, on my left, and you are number 2. And you guys are number 3, 4.
Is this continued training or once the training is done?
What do you mean? Well, your face, obviously. Say again?
As you train it, you first train, you finish it, and then goes and does something else. You don't
I'm just storing temp.
use data from the 1 and 2 to really train 3.
No, that's true. So it's all the categories are completely independent. In fact, I'm pretty much training a pause and window classifier on top of the second last layer of this network. Okay, so it's a very simple template-based classifier. Okay, so you guys are 8. So I'm going to move the camera back slowly. 7, 6, 5. Okay, you're F, right? 4. Okay, I'm moving a little too fast. If I move too fast, the camera gets blurry, and then 2, 1. Okay, and I'm still Yann. And this is still the water bottle. Still telephone. Still chalks. All right, and that's still rubber band. So let me, change the rubber band. No rubber band anymore. Oh yeah, still rubber band. Oops, not so sure. Here we go. Say again. So if I rotate, so let's say, I just kind of changed the rubber band. It's still the rubber band. So let me see if I can rotate. So that's still sort of a rubber band, it's kind of low scoring, but it's easy, right? It may not work that well for the telephone because the telephone really has a particular aspect ratio. So if I rotate, it's going to lose it. Okay, so if I wanted to be able to recognize the telephone, the rotated telephone, I would have to train multiple instances with rotation. Same with the face. I think it can tolerate maybe 20 degrees or something like that. I could easily make it completely rotation invariant by essentially applying the same network to all rotated versions of the image every 30 degrees or so, and then take the winning score, right? That would be easy. I'm not doing this because it would run too slow. It would run really, really fast on the FPGA board that I showed you. Say again? This is actually written in a dialect of Lisp called Lush, which I also developed. Which is open source, so you can use if you want. Yes.
In your architecture, there's no sense of time.
There's no sense of time. This is frame by frame, independent recognition. So we used a few more tricks in the system using this little feed-forward architecture I was telling you about. Some pyramid pooling and various other tricks. And I'm not going to go into the details of this, but eventually we got to about a little over 70% correct. So that was great. Except that at the same time, okay, so let me show you this a little bit. So this is another data set called the norm data set, which has more training samples of objects like this and fewer categories. And here what we did was that we varied the number of training samples in the training set for labeled training. And we plotted the error rate that we get when we don't learn the filters, and when we do learn the filters with various unsupervised and supervised and blah, blah, blah. And with and without normalization, etc. And so the Caltech 101 regime is this. Okay, so the Caltech 101 regime, it doesn't make any difference if you learn the filters or not. It makes a little bit of difference, but not much. Okay. Whereas as you increase the number of training samples, then learning the filters actually makes a huge difference. Okay, so Caltech 101 is a bit of a outlier. The data set is so small, you really can't say anything. Right, so here's what happened though. While we were working on this, another one of my students, Ilan Bourreau, who was collaborating with Jean Ponce in Paris, started to recycle some ideas that we developed in the context of those convolutional nets to improve the performance of Lana Lazebnik's system that was getting 65% before. And so instead of using k-means for the second layer of feature learning, she used sparse coding, the same technique that we used that I just described. Instead of doing this k-means or sparse coding on single CIF feature vector, she did it over neighborhoods to combine spatial information. She refined the pooling algorithm and all that stuff. And all in all, she got 75.7% on Caltech 101. So, so by the time we kind of catch up with the sort of handcrafted system, the handcrafted system gets better. But I can claim victory anyway because I was on in my lab too. So, yeah. And the idea of using sparse coding actually comes from, several people have used this idea of using sparse coding for mid-level feature learning in vision. So Ilan is one of them, but also Yang et al. At NEC. So this is a team led by Kai Yu at NEC, who is very active in this domain. So the next thing we did was the training that we have so far is a training that is at the patch level. So we do the unsupervised learning. We see each patch independently, and we try to encode, reconstruct every patch independently of other patches. But the whole process is convolutional in the end. So it seems like a waste to sort of learn all those filters and reconstruct the patch individually. So quite a few people had the idea of using something called convolutional sparse coding. Particularly my colleague Rob Fergus and some of his students and postdocs. He calls that deconvolutional networks. That was published at CVPR this past year. And there's sort of various versions of this for Boltzmann machines and things of that type. And there's this paper by Larry Carrion on sort of deconvolutional network as well that I was mentioning before. So here is the problem. If you train a sparse coder on isolated patches of images, you get shifted versions of the same filter multiple times, right? So these are essentially all the same Gabor filter at different shifted versions within the patch. It's kind of stupid to do this because you're going to apply those filters convolutionally in the first place. So you're basically going to have the same feature at multiple times it's really not a very good idea. So instead of doing sparse coding where you take a feature vector for one patch, multiply it by a dictionary element and sum that up over dictionary elements to reconstruct, we're going to replace a particular component of the feature by a whole image, a feature map, essentially. The operation here, instead of being a matrix scalar, a vector multiplied by a scalar, is going to be a convolution kernel convolved by an image. Okay, so we take an image, a feature map, convolve it with this convolution kernel, do that for all features and all kernels, sum them up, and that's how we reconstruct the image. Okay, so this thing. Basically, just replacing a linear operation by a convolution. I mean, it's also a linear operation. It's just a special type. Okay. And if we do this, it works much better. I mean, it looks much nicer. The features, instead of being those simple Gabor filters, are much nicer features. You know, they have things like endpoint detectors, like cross detectors, like little things here. I'm not sure how to characterize that, like center surround detectors like this. So much more diverse filters than what you get using patch level training. Okay. So that is really great, and there's some more examples of that. And in fact, if you have a single stage object recognition system, and you train that on CATTEC 101, it improves the performance quite a bit, from low 50s to high 50s. But if you add a second stage on it, the improvement is much less impressive for some reason. So it's kind of a little disappointing. But it works much better for this other data set called CFAR10. So that's a data set that was put together by Fergus, Antonio Torralba, who collected the original data, and then it was labeled by Jeff Hinton's team in Toronto. These are 32 by 32 color images with 10 object categories and 50,000 training samples total. Okay, so it's kind of like MNIST for objects, if you want. And here we trained that convolutionally also. Got something like 78% correct, which is just about as good as anyone has ever gotten on this. There's some unpublished results from Jeff Hinton's group where they get about the same performance. We also applied this to pedestrian detection, and this is a whole bunch of ROC-like curves, if you want, for pedestrian detection, where you set the false positive rate per image. So the number of false positives per image, so here it's set to 1 on average. Okay. And you measure the percentage of pedestrians that you miss in total. Okay. And the best performance system at the moment is about 8.7% or so miss rate for one false positive per image. And our best system with unsupervised pre-training and supervised refinement is at 11%. In fact, I got news yesterday, essentially, that we got below the state of the art, but it's unpublished results. This is going to be published at NIPS next week. And there's a big gap between this system, which is pre-trained unsupervised, and that system, which is just trained supervised without unsupervised pre-training. So that's one example of a task where we get state-of-the-art performance, and unsupervised pre-training is really required for that. Just the supervised stuff doesn't do it.
Why is one false alarm per image the operating point?
It's what people, look at. It seems like a lot. Yeah, that's true. It's actually not that high when you look at the images. Also, you can use all kinds of tricks to, this is raw performance per image. But then, if you want to put this in a car to do pedestrian detection, you can use tracking and all kinds of tricks, right? Motion, all that stuff. So you can work a lot better than that. These are a few examples of detections, and including people who are kind of really sort of crammed next to each other. There's a few misses, and the false positives, like this statue is a false positive technically. Okay, let me skip this in the interest of time and. No. I just want to say something about robots. Okay. So a few years ago, we had a project called LAGR. It was DARPA project. LAGR means Learning Applied to Ground Robots, or ground robotics. And DARPA had a bunch of teams involved in this program, and gave each team 2 of those robots, which are outdoors mobile robot about this tall, about this big. They weigh about 100 kilos. And the goal of this project was to build vision systems based on learning, essentially, that would allow this robot to drive in nature. And so you would punch GPS coordinates on the robot, and the robot would have to drive to those coordinates as fast as possible. Okay, possibly training itself on the way to do a good job. And you can use stereo vision for this. The robot has stereo cameras, so you can use stereo vision. The problem with stereo vision is that it's got limited range, so you can see things and tell whether they stick out of the ground up to about 12-15 meters, but that's about it. Beyond that, you don't get good enough depth information to really tell if something sticks out of the ground or is just something on the ground. But what it tells us is that for things that are nearby, like this bench and whatever, and those people, the stereo vision can tell us if something sticks out of the ground and we can't drive over it. All right. So what we're going to do is we're going to use the information from stereo to train a long-range monocular vision system based on convolutional nets to discriminate between obstacles and non-obstacles. Okay. And the convolutional net is going to be trained offline first, and then refined on the way as the robot drives itself. It's going to train itself with the labels produced by stereo vision. If you just rely on stereo, particularly short-range stereo, it's like driving in a fog. It's very difficult to know where you are and figure it out. So rather than showing you slides, let me show you a video of this. So this was done in collaboration with a small company in New Jersey called NetScale Technologies, which is filled with former AT&T and Bell Labs colleagues. And this is the robot driving itself around, and the kind of environment that we're supposed to be able to deal with. So the robot has two stereo pairs of two camera pairs, and the reason for having two is just to have a wide enough angle of view. And 4 computers in the belly. Is completely autonomous, so it doesn't use any information. So here it's sped up 3 times, and it only has a short-range vision system. So it has to get pretty close to this wall of people to decide to veer off. Same here. So here has a very, very short-range stereo vision system that only looks at 2.5 meters. And here we turn on the long-range vision system based on convolutional nets, and it sees the wall from the start, veers off right away. The goal is behind that wall here, but it knew to avoid it from the start. Same here. It veers off right away, and it's seen this wall of people from the start, and the goal is behind, back there. So the long-range vision system is one of those convolutional nets, and it's trained first in the lab on log files using labels produced by stereo for short-range things. And so we extract bands from the image that's sort of horizon leveled, and then feed these bands to these convolutional nets. And the convolutional net gives us a feature vector for every little window in the image, if you will, that we're going to feed to the last layer, and the last layer is going to be trained online. It's you can think of it as a linear classifier. And so the input is color, YUV color. So stereo vision gives us the labels up to about 12 meters, and we use that as training samples on the fly while the robot runs to train the long-range molecular vision system, and then we apply the molecular vision system to long-range to the entire image, and it's able to label the entire image and tell us that there is a little passageway here, and that's a hedge that you can't go through, and things like that. And so green is traversable, and red is obstacle, and purple is the foot of an obstacle, so it's kind of the transition between the two. And so it's able to really do a good job at sort of doing long-range identification of traversable areas and label all the trees and whatever. So after this process, we can map those traversability labels back into a map around the robot, centered on the robot. We call that a hyperbolic polar map, and do planning in that map to figure out where to go next. And in fact, we had to implement 2 separate vision systems. One, which this long-range vision system that runs at about 1 frame per second because it's very big, and another really fast one that runs at 7 frames per second that looks at very close range, very low resolution, just to avoid nearby obstacles really quickly, or people jumping in front of the robot or things like that. So that's kind of and we have to combine those two things. There's also visual odometry, which I'm going to skip. There's some learning taking place also in the controller. So the way we kind of drive the robot around obstacles is by having stored a dictionary of possible trajectories that the robot can follow. Question? Say again?
What if you have teeth?
If you have what? I'm sure.
Holes.
Oh, holes, I see. So actually, that wasn't part of the project. DARPA told us from the start, no holes, no water. Okay, they probably didn't want the robots to be destroyed. But it will actually avoid holes because holes are scary. It can't identify them, so it will just stay away from it. So this is an example of navigation. So this is to show the controller. So here it's only short-range vision system. The long-range vision system has been turned off. And this is my student Pierre Samanet, who at the time was actually an engineer at Netscale Technologies, and a PhD student with me. And this is my student Raya Hetzel, who worked on this vision system. She's now a researcher at Sarnoff in Princeton, and they make the life of this poor robot impossible, but eventually give up. And they're pretty confident that the robot is not going to run them over because they actually wrote the code. The joke is actually that's the way I select my students, you know.
That's a selection bias.
I put them in front of the robot, and if they survive, I keep them. So that's it. Thank you very much. No, it's just the DARPA wouldn't let us run it faster than that. So the robot mechanically can run at 2 or 3 meters per second, 2 meters per second, something, but they limited the speed to, I think, 1 meter per second or 1.2 meters per second, which is sort of fast walking.
But the code isn't a bottleneck.
No, the code could run faster. And now with, so now we have implementation of this on the FPGA board, which runs at basically 30 frames per second. So now there is really no limit to what we can do with this. We also have implementations of this in CUDA, also using GPUs that runs quite fast. So we could redo this project. So this is, this project ended a couple of years ago, and we could redo this project now with basically one small computer with either a GPU or this FPGA board next to it. It would be about this big. It would run much faster than this. We wouldn't need this, dual vision system. Basically, we could run the long-range vision system and just use that. It would run fast enough. Compressed sensing, yeah. Not really. I mean, yes and no. So you can make the argument that, the manifold of natural images is fairly low dimensional, and so with maybe the intrinsic dimension is fairly low. So with a small number of random projection, you can pretty much have all the information that's useful. Okay, but but first of all, it's not true that random features are good. They're only good for Caltech 101. For this other data set that I mentioned, you're much better off learning the features. And same for pedestrian. Actually, I didn't show the data for pedestrian with random weights, but it works much better in that case because you have more training samples. So you really want to learn the features, but you can still make the argument that perhaps random features do things that are not entirely stupid because of arguments from compressed sensing. But I just wouldn't recommend using random filters. That's a really bad idea.
So when you have a lot of training data, what is the difference in performance between initializing your weights in an unsupervised manner versus initializing using some flat random?
Yeah. So I wish I had a complete answer to that question. So I think it depends on the problem, really. So for things like pedestrian detection, it's a fairly big difference. It's just the difference between the continuous purple curve and the dashed purple curve, right? So for one false positive per image, it's the difference between 11 point something % error and 14.8% error and 11.5% error. So it's 20% improvement in error rate, which is, in miss rate, which is not bad. For Caltech 101, 1%, because the data is so scarce. In general, I don't have an answer. I really don't know. So other people have done more systematic experiments with this, particularly with fully connected nets. So the thing with convolutional nets, particularly if we use this, local contrast normalization, there's already a lot of prior knowledge built into the architecture that, helps it solve the problem. So to some extent, we're kind of shooting ourselves in the foot because the system is already sort of built to solve that problem with the sort of prior information. But people have done systematic experiments with fully connected networks. So things where it's a traditional neural net with, we have input layer and hidden layers and full connection between the layers. And there, if it's very deep, unsupervised learning really helps a lot, like a huge amount.
How does your offer compare with the DARPA Grand Challenge winner?
Oh, well, so the DARPA Grand Challenge is a completely different problem. The Grand Challenge was it was an engineering project. It was not research, really. Okay, it was. So the techniques that were used in the winning entries for the Grand Challenge are completely well-known techniques. They're very nicely put together. I don't want to, diminish the achievement of it, but from the point of view of kind of vision algorithms, for example. It's very simple. So for example, most entries in the Grand Challenge didn't actually use vision at all. They used LiDAR, which gives you range. So that's, it's much easier to do obstacle avoidance if you have a 3D reconstruction of the world around you. So CMU, for example, just used a CMU style solution, which is to build a custom super high power, long range, gimbal mounted LiDAR that would fry your retina if you pass in front of it.
The LiDAR you're describing, the LiDAR you use, this is really a LiDAR that can see kilometers, not a LiDAR that can see.
Well, so the CMU LiDAR could see, pretty quick, pretty fast and fairly long range, but you didn't want to stare at it. And the Stanford team used a combination of traditional commercial LiDAR plus a very simple vision system that used essentially color segmentation. So they would figure out what's right in front of the car. Right now I'm on the trail, so what's right in front of me is traversable, right? So I build a little Gaussian model, not even a mixture of Gaussian, a single Gaussian model of the color that's in front of me, and then I segment the whole image as to whether it's in the Gaussian or outside, and it basically draws the trail, okay? So it's driving on trail. If you go off the trail, you don't risk much except in a few instances because, it's basically a desert all around. There's one instance where if you go off the trail, you actually fall in the ditch, but other than that, no. And, you can use simple color segmentation. You're allowed to use LiDAR. So it's basically a big system integration problem, an engineering problem. And again, I don't want to, diminish the effort or, it's very cool that they managed to do this in such a short time, and it worked so well and reliably. But it's not science; it's not research, really. So this is where the LAGO project was much more challenging in terms of vision. We couldn't use LiDAR; we could use only cameras. It was off-road with annoying things like vine and tall grass and sand and all kinds of stuff, right? And trees. So it's a completely different problem. So the GPS only gives you, garden variety GPS gives you an accuracy of about 10 meters. Yeah, this was with GPS coordinates, and you won if you got within 5 meter radius or 10 meters or so. So yeah.
The quantification of the U of the coefficients, is that somehow related to non-negative matrix factorization? Are your matrices always positive?
Well, so there is some connection between sparse coding and non-negative matrix factorization, except the sparse coding we use has no constraint of non-negativity. We construct with the negative numbers as well, right? The rectification comes after. And so, I mean, there is an argument.
Solution might be that you could proceed as a hack algorithm for negative matrix factorization.
So it's not a hack. I mean, it's a hack in the sense that, you know, we put it in, it works better. We take it out, it doesn't work as well. So in that sense, it's a hack. But if you think about it, there is a very good, you know, justification for it a posteriori. So if you have an edge detector that you pass over an edge on an image, the filter activation is going to go from positive to negative to 0, right? From 0 to positive to negative to 0. It's going to follow the shape of the filter pretty much. Well, maybe not that way if it's a real edge, but if it's kind of a spike, if you want. So the next layer up is this pooling layer, which computes an average of the filter outputs, you know, transforms to nonlinearities over an area. And so because of these positive negative responses, you're going to get some cancellation. And so at the end, unless you rectify, those responses are going to cancel each other when you pool. Okay? So you have two solutions. Either you do average pooling by averaging over filter response over space, but you have to rectify. Or you use max pooling. So you just pick out the max activation of the filter in an area. And either of those two works. So people like Tommy Poggio, for example, prefer max pooling. We tend to prefer rectification and average pooling. But my student, Ilan Bourreau, the same student who's worked there, has done a theoretical analysis of which pooling is preferred depending on which situation. It turns out if you have very sparse features, you're better off using max pooling. If you have less sparse features, you're better off using average pooling.
You mentioned that your convolution filters are related to things people see in visual cortex. I would agree that maybe shapes, but how about spatial resolution? Is it also consistent?
No, so the visual system of humans, at least, is built in such a way that you have much higher resolution in the center than in the periphery. The resolution decreases geometrically, right, as you go outside the periphery, which is why you have to turn your eyes to a particular object to be able to recognize it. In fact, there are very, very good studies of this. There's a colleague of mine at NYU called Dennis Pelly, who has done a lot of experiments with, getting people to recognize objects that are not in the center of the visual field, and it turns out we're very bad at that. And it's not because of resolution. We have plenty resolution. It's just that the bandwidth of a visual system is just not good enough for that. But that's only true for humans. It turns out rabbits have very different space variant resolution from what we have. Rabbits, so the high resolution region of the visual field in humans is called the fovea, right? And in rabbit, the fovea is a horizontal band. Okay, so they have high resolution everywhere near the horizon and lower resolution up and down. And the reason is because they want to see they have the eyes on the side, but they have high resolution all around, and because they want to see the fox chasing them at high res.
Well, they can't see a hawk coming from
That's right. That's true. So the hawks, by the way, have two foveas. They have one in the front where they get stereo vision, and they've got one on the side just looking directly out, probably for navigation stabilization, I suppose. So there's no. The bottom line is that it saves you time if you do space variant resolution, but it doesn't. It doesn't allow you to solve the problem if you couldn't do it before. All right.
If you were trying to do a grand challenge, which you're not, it would seem like it might make sense to not do research, but to do basically solid development work.
Yeah.
Right?
Yeah. Yeah, that's absolutely right. Yeah. I mean, careful engineering. I mean, there's nothing wrong with that. See myself as an engineer as well. But, you can only have so much fun in one day, right?
Thank you very much.
Thank you.